All right.
Okay, so I'm going to have to pick up the pace a bit because apparently I'm running out of time. So some of the state-of-the-art features we're developing for Fledge. Like Marlene asked earlier, so when we try to go beyond Kubernetes, what do we do and how do we do it? So basically what we have by now is it can operate standalone without actual Kubernetes master node to run it. This is basically just a different front end for Fledge so that you can, for example, give it deployments via by loading them in from a hard drive or through a web API or all kinds of other options. It's not a full orchestrator quite yet. For this, we developed the orchestrator so swirly, which is basically a fully decentralized orchestrator, which is going to be discussed shortly after this. And we also developed a different networking solution, which is basically not, well, container networking VPN tunnels, but CNI warrants. So basically a combination of fully decentralized VPN and a container network, which is basically, yeah, ad hoc. So whenever they're required, some tunnel between two nodes is set up to exchange information or data. And once it's not required anymore, it gets torn down again. This is mostly done by allowing the nodes to discover their neighbors, build up their own environment, and whenever they need to communicate, they set up a quick tunnel, send some data, and get it back down again. We also have multi-runtime operation. So like I said before, at first we only had Docker and Containerd, which were basically both container engines. Right now, we're also working on OSV support and WebAssembly system interface. OSV support is actually already mostly underway and fully OCI compliant. So we can actually use the Docker container registry to also store micro VM images and get them from the registry and deploy them. Looking a bit more into the networking option. So this actually uses eBPF, also used lately by Sylvian Calico, for example, for their networking solutions, which are also used in Kubernetes. It's basically a kernel level insert, which may actually operate slightly below the kernel, or what's, or actually slightly below system calls. And they can bypass most default processing. Written in restricted C, and I mean really very restricted C, with extremely strict security checks on what you can and can't do. For example, you have to check every single byte of memory you use, or the compiler, the interpreter simply throws an error and your program stops. And that's it. So how did we implement these CNI warrants with eBPF, or rather, how are we implementing it? So like I said, it's nodes to node. There's no centralized controller, no cloud routing. It's, well, not just fully decentralized, but entirely masterless. Every node manages its own networking, its own VPN tunnels. It's self-organizing. Due to the eBPF, it's also very fast, quite secure. And when one node goes down, or one node gets compromised, the rest of the system just continues on working like normal. So what we're going to look at in the next slide is, for example, how does eBPF apply to when a Docker container communicates from its machine through the internet. So first, what happens with a regular VPN is, well, basically your container tries to send some data. You have to go all the way from the top of the OSI stack to the kernel. Then you get to the bridge, you go all the way up, all the way down, well, all the way up to the third level, then back down again, back to the kernel, to the tunnel device or the tab device that your VPN uses. Once you get to the correct layer, it gets encapsulated, but then it also has to go back down to the kernel again, has to go to the physical interface, and you have a huge path of network traffic all through your system through various interfaces. So what eBPF actually does is bypass basically everything. You can simply have your container traffic intercepted at the bridge where all the containers communicate through. You can encapsulate it at the kernel level before it even gets into the network stack. It does not show up in network monitors, traffic monitors at all. You can't even see it. And from the bridge, it gets emitted by the kernel to the physical layer of to the physical layer of the actual physical system interface directly. So you bypass the entire stack of the bridge, the entire stack of tunneling, the entire stack of your physical device even, and it goes directly out of the system, which is very performant and also very secure because there's no interception of the traffic anymore on your device. So basically how the multi-runtime operation works. Imagine you want to deploy something, so the Fledge API receives the deployment, but you're not quite sure how it should be best run on your device. Maybe you want performance first, you want just low resource use, want security, stability. So there's a runtime selector, which looks at both node capabilities and node current status. So to see if there's actually still sufficient resources available. It also gets the image from the image repository, or rather the metadata, to see all the supported formats. Then it picks whatever, well, for the moment it's just OSV or container, but then it picks whatever image format is most suited and sends it to the correct runtime to actually execute on the device. Like I said, right now it's containerd and OSV, but something we're going to work on in the short-term future is also WebAssembly support. Coming to the orchestrator I mentioned earlier, so we have basically the organization on individual devices, but we still need to orchestrate the devices on a higher level. We still need to orchestrate, well, basically entire software architectures rather than individual services. For that, we developed Swirly, which is basically a fully decentralized edge orchestrator. So also developed for the edge. It took some concepts for Kubernetes. It uses the Kubernetes API, but only the parts that are required. So you can just give this thing a Kubernetes deployment, and it will take care of it. And basically everything is supported. Resource management, resource use, resource limits, volumes, networking capabilities. It's all possible because it uses Fledge as an actual runtime. This thing is actually based on a theoretical model of node densities to determine where fog nodes should be placed and where edge nodes should be placed. Edge nodes in this case are just end user devices, whereas fog nodes can be interpreted as edge gateways that deploy heavier services. In this way, you can have edge devices that have certain requirements, and so Swirly will make sure that each fog node runs the services that are needed to service those end users. You can actually use this to build a hierarchical system, an entire service architecture, because you can in turn just treat the fog nodes as the edge nodes and then continue on all the way to the cloud. The key features, of course, are, well, resource efficiency. It uses about 13 megabytes of RAM for the entire orchestration level. Scalability, because basically this is almost infinitely scalable. It only handles its own neighborhood. So performance depends only on the density of nodes in its entire immediate neighborhood. But no matter if the network is the size of Belgium or the size of the planet, it will still respond in the same amount of time, the same latency, the same throughputs, the same management responses, basically everything. It can also work in real time, mostly due to, again, only working on its own neighborhood. It doesn't have to consider the entire architecture, the entire global system. It only really cares about its own little part of the software architecture. And also, it doesn't require micromanagement anymore, because you can just give it a service and say, like, make sure everyone has it, make sure it's available for enough people, and it'll take care of it. Also tried and tested, but yeah, that won't work. So, like I said, it's very performant, but it also needs to be accurate, of course. But globally, it is almost as good as a centralized solution. So when we look at edge to fog distance, which can be one of the factors for end user experience, we see that the theoretical minimum, which is something that technically even the best centralized solution cannot achieve, And we compare it to Swirly. Okay, the average is a bit higher. Swirly, by the way, is a centralized architecture. Swirly is the decentralized architecture. So this is something on the order of 98% efficiency that you can practically achieve. This is very close to it. What we saw, however, is that some nodes go way up there because it is a decentralized solution. It doesn't know the entire global picture. So some nodes will always have bad performance. And that is definitely something that we still need to work on. I'm champion of silly names. So basically, Swirly was very reactive. It gets data from edge nodes and then decides how to orchestrate the fog nodes, what services it needs to deploy and where. So we basically wanted to make this more reactive. To make it more reactive, we developed predictive components to learn user behavior and improve quality of experience for users. One thing, this had to be done in the edge, of course, so we had to kind of work with very small models and a new approach of actually designing these models and training them even in the edge. So basically, there's two parts to it. The one part learns QoE factors, or rather which dimensions of user behavior, surface behavior, and device properties are important for quality of experience, and how they should be weighted. And the second part actually predicts quality of experience in the short term, which is up to minutes, for individual devices and services. This is, for example, the architecture to, well, basically the entire pipeline, where you see the QoE approximation and QoE prediction. It also keeps a cache of known quality of experience factors for specific nodes. And whenever node info is received, the cache gets updated. The edge device takes a look at, well, which is the best device to suit my needs, and then selects that device if it is still available. So in this architecture, the edge devices themselves can actually select which service provider they want. The optimal one may not be available, but since they have an entire cache of them, they can just take them in the order of preference. And if we look at the impact on quality of experience, so you see here the normal reactive versions, and this is the proactive version. So lower is better. We see that the reactive version actually has significantly lower median and actually most experience values. The top experience values are still the same because there's kind of a cutoff implemented that says, well, quality of experience can be this high, but no higher. So it doesn't always look for the better alternative. This is to avoid kind of switching between different servers constantly. But still, it's a significant improvement over the rest of, or rather over the reactive approach. And we also achieved our goals of running this in the edge, because as you can see, this barely takes about 25 kilobytes of memory. And it can run in, well, about 100 microseconds for a single sample. And batched, it's about 2 microseconds. On an NVIDIA Jetson Nano, by the way. So coming to decentralization. So we saw a decentralized orchestrator already. We have Swirly, we had decentralized networking. Of course, all of this has an impact on software design. You can't simply take your software stack from the cloud or your software architecture that you deploy in the cloud and expect it to work fully decentralized. You have to kind of anticipate how this sort of paradigm will react to your software. Nodes, for example, are self-governing, so there's no centralized control over what happens to what node. It's basically user experience driven, as we saw with the proactive approach that takes user data and device data and tries to give the user the best experience. And service architectures are basically self-organizing. Meaning that you work from the edge up rather than from the cloud down. When you deploy from the cloud, you basically put your entire deployment into Kubernetes or something similar, and it decides where to deploy what. Of course, when you work decentralized, you kind of work from the edge devices, which decide which services they need, and then go and look where they can find them or where they can request them to be deployed. So this is more involved than just having cloud deployments. You can, for example, have runaway service replication. If you don't watch out, if your load is too high, every node works for itself. So every node can, in fact, overload itself with the same and only service. And there is a lot of resource competition. You won't get globally ideal resource use, but as we saw with the benchmarks before, it's actually pretty close. And there are no high-level overview tools yet. It's not impossible to get some sort of global management, but it would be very difficult if you're dealing with hundreds of thousands of devices. The network traffic alone would probably kill your cloud. It's also not always applicable. For example, don't design Microsoft Word as a fully decentralized application. Decentralized networking. So as we saw before, there are some aspects of networking that are still mostly centralized in a lot of applications. Like networking itself is inherently decentralized, but then you have overlay networking, which still has cloud controls, centralized controls, management nodes. There are leader elections involved. In short, there is a lot of top-down control when we're dealing with service architecture networking. But we're working on it. We're trying to decentralize basically all of it so that we can have a fully scalable and functional edge. And another important thing for decentralization, of course, is learning. There has been some progress in, distributing learning, but not much progress in decentralizing it. Federated and hierarchical learning, for example, are great for distributing your learning. You can distribute all your learning samples over all your nodes, get it done a lot faster, integrate the results, and you have one finished model. But if you really want to decentralize it, there are some other aspects to consider. For example, there are limits to learning. For example, imagine that this house wants to get updates from other nodes for its artificial intelligence model. These nodes directly connect to it in its neighborhood will send some updates, and they will have a specific weight attached to them. These nodes have a significant impact on this central node, but the further you go away from them, the lesser their weight will be. So it's kind of a trade-off between, how many nodes do you want to communicate with, and how much of an impact do you want other nodes to have on the learning of any single node. But we'll go into more detail about that in the AI session later today. And then there's some, decentralized security and management. Decentralized management, of course, is difficult. Once you lose your dashboards, you have no control left. You kind of have to rely on the device to manage itself. So basically, you can have some device self-management. Devices and or software can assume zero trust. You have to ensure some optimal hardware security features. Also, resource availability once you select the sort of device you want to work with. You also need secure runtimes and minimal OS. And once you have the security part up and running, you can probably design a decent self-managing device. There's also a bit of self-management involved. So each node really needs to look at, is my operating system still working as intended? Is the hardware still functioning completely? Is there anything wrong with the device software, for example? And it can self-validate itself, grant itself a certificate of proper functioning. It can distribute this to the nearby nodes, which can independently validate its functioning, and then you can build up a sort of trust system between nodes, which can detect rogue nodes really quickly and shut them down from communication. And then just a quick project example of decentralization. It was introduced last time too. So digital cinema, in which we had several cinema halls that wanted to communicate on a common network, with the projectors generally having around 2 to 4 terabytes of memory, data storage, and a 10 gigabits network backbone. So basically you had a bunch of projectors in each cinema hall and different buildings around the country communicating on the same network. And now, instead of storing movies statically on each projector, they wanted a sort of system to exchange movies as needed, according to a specific movie schedule over that 10 gigabit backbone. So what we used as a solution to this was basically gossip algorithms in combination with promises. So the gossip algorithms basically propagate metadata and information about movies, specifically their availability, to the rest of the system. We use torrents to actually transfer the movie data, and the promises are basically a new system that, well, basically a node promising that it will make a movie available. So any node can have a number of promises. They don't have to be instantly available, but once a promise is made by a node, it has to keep that movie available as long as it has that promise. Using the promise system, you can keep a minimum of any number of movies in the system. You can also apply a maximum, but yeah, it's not really a maximum needed. It also always tries to keep around the minimum.
If I can give some context, the idea of the promises is that gossip algorithms, they don't give you a view of the system at that time, but they give you an eventually consistent view. So it could be that according to gossip algorithms, a certain node is still available and is still storing a movie, even though at this time it was storing that a few seconds ago, but at this time this node has crashed, for example. And that's why we can't simply say we're going to use promises, we're going to use gossip in order to figure out, okay, if this movie is stored on 2 nodes, if it's stored on 2 nodes and I am the 3rd node, then I can remove it because it's already stored on 2 nodes, because it could very well be that at the point where you remove the movie, one of the nodes has already crashed. You simply haven't heard about it yet, because gossip, it takes a while for messages to reach you. And so the idea of promises is that you basically try to find a way to make sure that the movie is stored at least twice in the cluster, even though you don't have a real-time view. Promise theory is a very interesting solution to make certain claims about, make certain assurances about your cluster, even if you don't have a real-time view of that cluster.
Yep. Okay, so just to show you how this actually disseminates information through the network. So one node has some information that needs to be spread through the network using serve. Gets to the neighboring nodes, then to those neighbors, and eventually the entire network will have the required information. The other project examples, well, we already saw about these. We go from individual devices to orchestration to federation of networks. So we'll skip over that. And in conclusion, well, there are tons of aspects to Edge IoT security, ranging from the device to the actual service architecture. You also have to consider the actual environment your device is operating in, and well, what your users will do, which is kind of difficult to anticipate. In Edge orchestration, there's a move to smaller devices. We're actually trying to get orchestration to work on, in a limited way on microcontrollers. Orchestration is moving towards decentralization. And we're working on scalable and secure and decentralized networking options. And in terms of decentralization, well, it's necessary, but or rather it's necessary once you start working with the edge and a larger scale. But there are trade-offs and considerations. So thanks for your attention.
If there are any questions about this presentation, feel free to ask them. Tom will also be here for the lunch, so you can also discuss the specific technologies during lunch.
Yes. At one of the first slides, you had said that the OSV integration was better than native performance. Yeah, could you quickly explain how that is possible?
Yeah. So OSV basically runs in kernel mode all the time. So basically any software that's run on OSV or any unikernel that's run with OSV operates completely in kernel mode. Even if you run, for example, a REST service, it never switches from user modes to kernel mode. It just stays in kernel all the time. So we have no context switching at all. So it just goes straight through everything.
This is
why it can be more performance.
This is also the reason why the sandbox, the Docker sandbox solution from Google, what was the name? gvisor. Why gvisor has such bad performance? Because it actually increases the the number of context switches for every system call that a Docker container in gvisor makes. The system call first goes to the kernel, then goes to user space to gvisor, then goes back to the kernel, then goes back to user space to the application. And so if you're talking about setting up network connections, for example, an incredibly big overhead of that are these context switches. And so by reducing the context switches, you can have incredible performance improvements, and by increasing the context switches, you can have incredibly bad performance. Even when you look at if this application would not communicate to the outside world in any way, would not spawn new processes, would only have single core processing, then inside of a unikernel, it would be a little bit worse because you have the virtualization, and inside of gvisor, it would be more or less the same, because you're not actually communicating with the whole gvisor part of the sandbox.
Yeah, there's also a bit of drivers involved, but mostly the context switching is also partially responsible for the performance difference between Firecracker and OSV, because OSV does not run entirely in kernel space. So despite the fact that they both use the same virtual I/O drivers, you can see that Firecracker is just a little bit slower than native performance.
What all the research activities are you doing in space, Tom? And maybe what is that people might be able to expect and maybe even participate on, or what you might be looking for?
There's also a couple of things in artificial intelligence. Well, actually, I covered most of it, but not really all the details. So that would take a lot more explanation. But in terms of artificial intelligence, there's a couple of slides this afternoon where I'm looking into new ways of building models for the edge. So basically different interpretations of mathematics behind neural networks, so that you can train models to like 1,000th of the size while maintaining decent accuracy. But what I'm mostly working on now is the CNI one.
Okay, thanks.